Okay. So good evening, everyone. So today we'll be discussing first reviewing what is Q-learning, and then going and discussing Q-learning with linear function approximation. It's a little bit of its convergence, and then asynchronous Q-learning. So Q-learning is one of the most fascinating topics in reinforcement learning because originally people set out to learn the Q value function because we'll see how advantageous it is compared to just the value function. So recall what an MDP looks like, or a control Markov chain look like. So you have a state, you take an action, you go to make a transition. The transition is based on this control probability matrix. Given a state and action, you know the probability distribution of going to a particular state. And you see a one-step reward. So the goal is to maximize this reward. Maximize long-term reward. We have seen it numerous amounts of number of times that's what we want to do. So what is a Q value function? A Q value function, Q of is defined from state and action to a real number. Okay, so this is like for every state and action, you return a real number. This is the definition of the function, and it is defined by this equality. That is the expected value of the discounted reward, for example, I equal to 0 to infinity, and the reward of S0, A0, or rather SI, AI, SI plus 1 given S0 is equal to S and A0 is equal to A. Okay, so this was our Q value function. Say if actions were sampled by a policy pi. So this would be for a policy pi. Okay, we have defined this previously, isn't it? So this is the total reward. Total reward given. What is given to you? The start state, and action. So I hope you all remember this. And therefore, let us try and write down a tabular Q-learning algorithm for a model-based setting. So what is model-based, RL? First of all, what is model-based, RL?
Where we know the transition probabilities.
Good. So we know that S dash given SA is known. And the rewards are also, the reward function is also known. SAS dash, the function is also known. Okay, so these dynamics of the Markov decision process or the control Markov chain is known to us. So let us try and find it out for that case first. So see, this is for the entire trajectory, right? So this is for the trajectory S0, A0, S1, A1, S2, dot, 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 dot. So, but I am being given only S0 and A0, and I want to write out a recursive function, and we have done this again and again. So how do we do that? We know that this can be written as the reward at S0, A0, or S0 is rather S, A, and say S1 plus the summation. This is S0, this is A0, as we have conditioned, you can clearly see the conditioning and it is known. Therefore, I'm just putting the values there. And then you have I from 1 to infinity, gamma to the power I, reward of Si AI, Si plus 1, given S0 is equal to S, A0 is equal to A. So now what do? I write down the we have done this again and again. So gamma times I equal to 0 to infinity, gamma to the power I, reward of Si plus 1, AI plus 1, and Si plus 2. Is this summation correct? Okay.
Yes.
So now what do? Once I know this, what do? Because this second term here is what are the random variables over here? What are the random variables?
It's Si plus 1, Si plus A.
Yeah, 3 is also.
Yeah, Si plus 1, AI plus 1, and Si plus 2, and I can condition over Si plus 1 and AI plus 1.
Yes, so this is over all the random variables are all these, right? S1, A1, S2, dot, 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 and so on, right?
Yes, yes.
Yes. So now I don't know any of these random variables, but I only know S A and S A0. So therefore, if I am going to condition, I have to compute an expectation. I rather take another expectation, a reiterated expectation, conditioning S1 is equal to S, right? So this is what I do. And this term becomes, so given that S1 is equal to say S dash, for example, S dash. So what can I write? I can write this as a double summation, a double expectation again of reward SA S dash plus gamma times. What is this inner expectation going to be? What is the definition of this? So the value function for a policy pi is defined as I equal to 0 to infinity, gamma to the power I, reward of Si, AI, Si plus 1, given S0 is equal to, rather given S0 is equal to S, right? So here it's the same definition.
Yes.
Starting from 0 or starting from 1 does not matter. Starting from 0 or 1 or t does not matter. Because the Markov decision process is time homogeneous. This is our assumption. Okay. So I can clearly write this as V pi of S dash. Again, we have done this before. So our two expectations again can be written as a single expectation overall the. Now, what is the only random variable that is remaining over here?
S dash. Because
So
I'm
S
summing the
dash is correct. So S dash is sampled from the probability distribution S given S and A. So S and A is given to me. Great. So now this is known to me. Okay. So now the Bellman optimality equation, what can I write? So let there be a policy pi star such that the corresponding value function is Q star. Okay. So say this is the, so let there be the policy pi star so that the corresponding policy, the value function is Q star, or the Q value function is Q star. So therefore, what can I write Q star to be?
I
Q
can
star.
first write Q star of S of A to be expectation of reward S A S dash plus gamma V pi star of S dash, and then I can write V pi of S V pi star of S dash as Q pi
Yes.
max of Q pi S dash A dash.
So this is fine. I just replaced pi to be pi with pi star. This is the step one. And as Antriksh is telling me correctly that V star of S dash means what? This is the optimal value function at state S dash. And that is basically what? This is basically the maximum action, right? So any action that maximizes Q star of S comma A, right? Because at any state, if you have action 1, action 2, action 3, dot, 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 action N, and you see that this action is giving you maximum reward. So you will always select this action, right? Always select this action. So therefore, we know that the value function for a particular state S dash is just maximizing over all the actions at that state. If you have, you will see whatever max action is maximizing your reward, that's your value function. Because in the optimal case, you will only select the optimal action. That's it, right? So now I can write this as Q star of S comma A as the expected value of the reward of SA S dash plus gamma times max of A dash Q of S dash A dash given S comma A. So now the tabular model-based algorithm, therefore could be, this is a Bellman operator. So I start from any Q0 and iterate. So a Bellman operator, just tell me what would be the Bellman operator? TQ, for example, TQ of S comma A is the expected value of, we have defined this before as well, plus gamma max of isn't it? This is your Bellman operator. And I'll keep on
Yes.
updating. I'll keep on updating Q. So I can write Qn plus 1. They say we'll see it's a contraction as well, and that will prove that it will converge to a unique fixed point by Banach's fixed point theorem. But we can clearly write this as, so first let us write out the Q star
Update.
expression. Yeah, let us write down the in terms of a summation. We know the model. Therefore, over all S in the summation in the state space. As you can see, this is only the random variable that is there. You can write this as the reward plus gamma times max of A dash Q of Q star of S dash A dash. Right? This is correct for everyone.
Yes,
I
sir.
just wrote out the expectation in this form. Great. So now, therefore, the iterative algorithm will be, the iterative algorithm is as follows. This Qn plus 1 S comma A is equal to S dash comma this A dash, where is dash. So here, this is already known to us. Everything is known to us. You can keep on iterative algorithm until convergence. That is fine. So if I have the table given to us, and if I have the, so if the states are finite, action is finite, if I'm given all these things, and I'm given a Q value function, so we'll end up with this iterative algorithm. So now, what is the advantage of using this?
Dada, I
Why
have a question.
not? Yeah.
So when we discussed the Q-learning method earlier in the with model-based algorithms, we had actually used the update equation Qn plus 1 equal to Qn of S plus.
Yes, because that was true. That was uh, that equation that we have was from the data. Here, we are not using the transition probabilities, right? That is model free. Like that's why I came back to this once again and tried to discuss it. That is fully
Yeah,
model
sorry, I
free.
got disconnected, I guess.
Yeah, yeah. So the algorithm that we discussed then was again a DP algorithm, dynamic programming algorithm. And then there too, what we had found out was that we were learning from the data, right? Like we did not use the probability distribution as given SA, right? We did not use that, correct? We'll come to that algorithm as well. But that was the introduction. There we were sampling the next state, right? You see in this equation, we are using P of S given S dash given S comma A. Yes or no? You are talking about this algorithm.
Dada, like I think he, yes, he joined.
Yeah.
I'm
So
sorry.
you yeah. So you are talking about this algorithm, right? So SA S dash plus
Yes,
gamma times
gamma.
max of.
Yes, S dash comma A dash minus Qn of S. Yeah.
We'll come to this algorithm. This algorithm is actually, you can clearly see it's a model free algorithm, right?
Yes, but like when you were teaching model based, you
Yeah,
used
when we started off, I didn't go into model based and model free. I went to model free once I came to uh, lecture 11 or 12. So when we
yeah,
first
when you
introduced this.
were doing policy iteration and then value iteration, then you when you mm, taught us Q-learning, you taught
Yes,
this.
I taught this because that time I was trying to correlate it with the bandits problem. We are using this.
Yes.
I was trying to, yes, so that's why both are actually the same. There's not much of a difference. But if you have the model, then you better use the model. So that's why I tried to bring all the Q-learning algorithms today into one footing, because that time we did not know what was a model free algorithm and what was a model based algorithm, right? Now we know. Therefore, it's good to understand.
Also, the nature of the previous equation allows us to like not do SATSA and go through every state at a time and then
Correct.
up.
It's like the value iteration and so on.
Right. So,
Yeah.
like in my head, I had thought that Q-learning is only SATSA, but here it's clearly we can make it iterative as well and not SATSA.
Iterative. Correct. And we will see synchronous. That's why today we'll see a lot of variations around Q learning. Therefore, Q learning could be along trajectories. It could be allowed iterate across state and actions in a for loop. It could be synchronously updating all states and actions, or using an entire trajectory to update states and actions, as we have done here. We'll see. Okay.
Yeah, okay.
Yeah. So there's a lot of variations, and all of them are actually the same thing. I'll show you the proof of one of them. So that's a very good point that you brought up, and that's why I tried to clear all the doubts around this. So what is the advantage that you have over Q-learning over value iteration? Just finding the V pi star directly. So if you know V pi star of S is known to you, is known, if V pi star is known versus Q star of S comma A is known, which one would you choose? And why? I would definitely choose Q star because the action, the A star for pi of S is just the argmax of Q star of S comma A, yes or no?
Yes.
So the recall, the ultimate goal of RL is what?
To maximize long-term reward.
That is true. But what is the goal? Is control, right? Is
Yeah.
to get the best policy, isn't it?
Yes. Like in V star of S, we don't know which is the optimal action, but here we get the additional information that which is the optimal action.
Correct. So therefore you see V star of S that I have over here. If I have to choose actions, so from V star of S, if I have to get pi star of S, what should I do? So think that you do not have the Q star, you have only V star. What will you do? Very, very nice question for your, if you had an exam, I would have given this. How will I get the pi star? See, look at this Bellman equation.
I'll observe the actions which because this is if I perform the TPI operator, I'll get the same thing like TPI of VPI equals
Correct.
to VPI. So I'll make a state transition and I'll for a state S, I'll observe that which action is actually giving me the maximum reward. So it would be,
No,
I mean, that
not
would be,
directly. So see, Q star is related to V star in this form, right? Yes or no?
yes,
So now if I know V star, I know Q star as well. And I can compute it. Okay. Then I have to select pi star of S is equal to argmax of S, argmax of A, Q star of S comma A. Isn't it? So it's a two-step process. Clear? Rather, if Q was known, Q is known, pi star is known trivially. Okay? Fine? Is it okay, Antariksh?
yes.
So this is the advantage of Q-learning. So better, yeah.
I'll go through all the actions and then I'll see that make an array of q pi star s dash s comma I, which would
Correct.
be one cross action space, and then I'll select the max of that array.
Correct. So you will select for every state, you will see over all the action space and then try and get the best action. So anyways, you have to compute the Q value function if you have to calculate the policy, best policy. Therefore, people directly learn the Q value function. So now, today the ultimate goal would be something like this, where we would have a feature matrix for every state and action, and we would try to learn, as we had done like last time, a linear function approximation. I'm not going into this yet, but let us first consider a model-free method, as we had done last time, an alternative view to find out this model-free method. This is an alternative view. And since we have done policy linear function approximation, this will help us. Okay, let us try and find this. So say the loss function Q, for a loss function Q, let Q star be the optimal policy or Q value function. Right? So let that be the optimal Q value function. So therefore, say state and action are finite. So you can use a tabular learning, right? So for every state, S1, S2, dot, Sn, and A1, A2, dot, AK, I can have a value, yes or no? Something like this. Clear? That's just a tabular Q-learning algorithm. So now I say that I define a loss function. So this is the Q matrix as proportional to Q minus Q star whole square. The L2 norm of this. Right? I can do that. So for every element,
Yes,
I can for every element, and I have a Q star matrix as well, N cross K matrix and N cross K matrix. I will subtract both of these matrix, Q and Q star, and then I will take a element wise summation. So let us try and do that. So let's define L of Q as the summation of states and actions, 1 by the number of states and actions, Q star of S comma A minus Q star of or Q of S comma A whole square. I have a half here for normalization. So is this loss function equivalent? Clear? For all states and actions, I'm just adding them up, right? 1, 2, 3, and so on, till all the NK terms. Fine. Any question? These two are equivalent, yes or no? So if these
yes,
two are equivalent, so let's say I want to learn Q of S comma A or Q, the Q value function itself. What can I do? I can do gradient descent, yes or no? We have discussed gradient descents multiple times now, right? I can learn Q iteratively. Gradient descent. I can do that. Okay. So I can say that Qt plus 1 is equal to Qt minus alpha t, the gradient with respect to Q, L of Q. I can do that. See, this is the loss function and this is the variable. Q is the variable. So I'm just updating the values, variables at these values. Is it fine?
yes, Dada.
Okay.
But one question,
Yeah.
like last time when we were doing it for the linear approximation, we had taken the The stationary distribution probability, d pi.
Correct.
Now,
Correct.
you have taken 1 by number of states into number of actions, which is also correct.
Very good question. Very good question. I am taking a synchronous case. We'll come to this. This way your doubt will be solved. Synchronous because all states and actions are being updated together. Okay. That's why we don't have a behavior policy yet. When we come to asynchronous algorithm, we'll see the behavior policy. Okay.
Yes, sir.
Okay. So here we'll come to the algorithm more interpretation, and then you'll understand why this will also work. So let's try to take a derivative of with respect to q of this function L of q. Okay, so let's take it for one value. So dl dq of s comma a. Say I take it for one value, right? So what is it equal to? Minus 1 by sa q star of sa minus q of sa. Yes or no?
Yes,
This
sir.
is the derivative. This is the derivative, correct. So now I will write qt plus 1 for s comma a as qt of sa minus alpha t by, rather plus alpha t by. So I'll for the timing, I'll write this as beta t. This will help us. Beta t s comma a q star of s comma a minus q of s comma a. Very nice. And I'll say that this is equal to alpha t. Qt of s comma a plus alpha t q star of s comma a minus q of s comma a. So in the matrix form or the matrix or vector form, what can I write? Qt plus 1 is equal to qt plus alpha t qt minus or q star minus qt. Is this fine? For all states and actions? These two are equivalent. This is a single value and this is for every state and action, for all states and actions. States, comma, actions. For every state and action, you will have this same update. Correct or not? Okay, so I have derived this algorithm. So now you tell me what is the problem with this algorithm? The gradient descent algorithm. Can you tell me the problem with this algorithm?
I don't think we know Q star initially.
Correct. Q star is not known. So can it be implemented? Not directly. So now if it is not implementable, so let's try and derive a stochastic gradient descent sort of an algorithm. This is full gradient descent where every state and action is being updated. We'll see what to do with respect to when we do not do that. So we'll try and get a stochastic gradient descent update. Let's try to get that. So let us first write q star of s comma a as the expected value of, what is it? S
Reward.
a.
Yeah.
Yeah,
Plus,
this
yeah.
is fine.
Gamma. Yes, it's fine.
Very nice. So s comma a is given. Okay, so now I tell you, if this is known to us, I will say q star of s comma a minus q of qt of s comma a can be written as the expected value of reward s a s dash plus gamma times max of A dash Q star. So this is a constant, right? This is not in the expectation, right? S and A are both known. So basically what I'm trying to say is this. S dash comma A dash minus QT of S comma A. I can write this. This is equivalent.
Yes, Dada, because it is a constant.
Yes. So I will write this over here as well so that you will understand. So QT of S comma A. So this is the constant because S and A are given to us. So I can take it inside the expectation. And the only random variable here is S dash sampled from the Markov decision process. Now, very nice. So this is what my gradient descent, the update is, yes or no? The value of the gradient. Do you agree?
Yes.
The value of the gradient is this because this is equal to Q star minus QT. So as soon as I see an expectation in a gradient, what can I do?
I can take the expectation out and make it stochastic gradient.
Correct. As soon as I see an expectation, in gradient descent, just use the stochastic term for SGD, the stochastic gradient descent. So therefore your update becomes QT plus 1 S comma A as QT plus alpha T R of SA S dash plus gamma times A dash Q star of S dash comma A dash minus QT of S comma A. So again, here the problem still persists, right? So this is your model-free tabular Q-learning. Right? So we are categorizing first as model, tabular, free, based, yes, no. This is what we are trying to do. So we have done till now, we have done tabular and model free, tabular and model free, and we have done tabular and model based. Okay, so this is model free. Okay, fine. So once I have this algorithm, again, the problem persists that Q star not known. Fine. This is not known to us. So, but we can show that we will show, in fact, we can show that Q star can be replaced by QT. Okay.
No, QT. Yeah, sorry.
QT plus alpha T reward of SAS dash plus gamma times max of A dash QT SAS dash minus QT of SA. And still this algorithm converges as T tends to infinity to Q star. Okay. This can be shown. We will in fact show it in a while. So now this is Antrix, this is the algorithm that you were talking about that we had found out.
Yes.
So this is
Yes.
an alternative way to look at it. So it's a model free algorithm and we found it out using this, and it's also called synchronous Q-learning. Why is it called synchronous Q-learning? At every step, all states S comma A are updated. Only sample S dash based on this distribution for all S comma A. Is this clear to everyone? So what am I doing at every step? Sorry. At every step, I'm running over all states and actions, and I'm sampling the next state as dash, and then updating every state like this. Is this clear? So what am I doing? I'm going S1, A1. Then for state 1 and A1, I sample S1 dash as, okay. Similarly, S2, A2. See here, there's an indexing problem. Wait, I'll not introduce this problem. Wait. So we have been using S1, A1 as times, right? These are random variables. So how do I represent states as number 1, 2, 3, 4? Here there are two random variables, right? We have S and we have time. Time is the time points we are updating. Wait, I'll just tell you what I mean. This is done for all states and actions. So now, here as well, I have used S1 to Sn. Please note, these are not time points for the Markov process. Rather, I'll use a different notation. So say the state space S is 1, 2, 3, n. And the action space is A, B, C, dot. Or rather, let me write like this. A, B, C, dot, Z. Not. So ABC will also not be fine. So let me write alpha 1, alpha 2, dot, alpha k. This is fine. Okay. So say these are the states and these are the actions. So I'm saying for every pair 1 comma alpha 1, this is at state, at time 0. Similarly, 1 comma alpha 2 all the way to 1 comma alpha k. You will sample time equal to 1. Say S1 is equal to 3. Say state 3 is being updated, right? Say the next state S dash is 3. So what your update equation will look like? Can you tell me for this? The first time point Q1 of 1 comma alpha 1 will look like
Q1 of Q1 alpha 1.
Q0 of alpha 1 comma alpha 1. The first
Yes. So Q1 of
initialization
alpha 1 is equal to
plus
Q0 of 1 comma alpha 1 plus alpha. We should denote it by, I guess.
okay, I'll
Not
just write lambda
yeah.
lambda 1. Okay.
Yes. So
So
Q1 1 comma lambda 1 equals to Q0 of 1 comma lambda 1 plus alpha 0, right? or alpha 1.
Alpha 0.
Alpha 0 of R of 1 comma lambda 1 3. Lambda 1 comma 3.
Lambda 1 comma 3. Very good, because this is the next state S1. This is S0. Very good.
Gamma of max of
Over
alpha.
all actions.
Yes. Lambda dash or A dash, whatever.
U0 of
0 of
3
comma
comma A.
is
Right? This is the
is
S1 minus Q.
0 of 1 comma lambda 1.
Good. So all I want to say is for every state, for here, this is synchronous because you write a for loop like this for all S in S, for all A in A, right? Update. So first sample. So I'll just write down the algorithm. Maybe it will be easier for you to follow. Synchronous Q-learning. This is the pseudo code. So for all, or rather, let me write for S in state space, for A in action space. What will I write? Step 1 is sample S dash as the probability distribution, this. Fine. Then select then Q of SA for t equal to 1 to n. Say let us write capital T for n time points. N times I will update, say I update n times for, or t times for convergence. Okay, so now what can I write this as? So this can be written as Q of t plus 1 is equal to Qt of SA plus alpha t R of SAS dash plus gamma times max of A dash Q T of S dash A dash minus Qt of. Is this crystal clear now? There are 3 loops over here. There's this outer loop is the iteration, and the inner loop is over states and actions. And this is update of Q function. Clear? Any questions? You can implement this now.
Yes, done.
So now I have discussed a implementable algorithm using SGD. Now I'll try and discuss the convergence of this algorithm. Very simple, not difficult at all. So let's try and see the algorithm once again. So what does algorithm look like? Qt plus 1 is equal to Qt plus alpha t R of t plus gamma times Vt minus Qt. Let us define each of these terms carefully. So this is equivalent. Why is it equivalent? I'm going to say. So remember Qt plus 1 for this is the expanded equation. This is the convergence results. expanded equation is equal to qt of s comma a plus alpha t Okay, so this is the equation I know. So now what I want to do is I want to write this above equation in a matrix form. Okay, so now I say if I can do that, I will write RT of S comma A. So RT is a, again, tell me the dimensionality of RT. What dimensionality should this be? Each of this dimensionality, tell me what is the dimensionality of QT? Belongs to which space?
R to the power S into A.
S
Mod
into
S.
A.
Yes.
Okay.
Yes.
So this is the space in which Qt belongs to, because I have S states and A actions. So this, if you stack them in a vector, it will be in this space. So now RT, what should be the dimensionality as well? Again,
Because it is control Markov chain, it should be a 1 cross uh, S cross A vector.
see, this is
Or
a
rather
vector
S cross A.
equation again. Yes, it's again a vector, correct. It's a vector equation, right?
Yeah, I said it's a vector with S cross A columns and
Correct,
sorry, rows and one column.
correct. Same. It's just a vector. No, if it's a vector means it's just always one column. So vector equation, all dimensions must be same. Must be same. So therefore RT has to be in SA, and RT we can define as to again reward. And how can we define this? See, RT of S comma A is equal to RAS dash. Now you will ask me, Dada, how is this possible? The right hand side is a three variable equation, left hand side is a two variable equation, two variable function. How are we even equating them? Can you tell me how are we doing that? See, the right hand side has three parameters, three variables. It has two variables. Does it?
No, actually, because it is a control Markov chain, we can sample a reward, but like given S and A, there should be a S dash because if it is a control Markov chain, we should have a definite S dash for an S and A.
No, it's a probability function again. It's not definite. So see, the left hand side is S dash is sampled from probability distribution S comma. Yes or no?
Yes.
Do you correct? So at time t, there will be exactly one S dash. Yes or no? Because you will sample at time t, one S dash. Correct?
Yes.
So what I'm trying to say is no, it's not a two variable equation. Here, the three variables are S, A, and T. Yes or no? Now it's clear. Therefore, there's this equivalence. This three variable only. Okay.
So Dada, like RT will be a means probabilistic, whether means at different times we will get different S
Correct.
dash means.
You will get at different times, you will get different RT. So you will have R1 of S comma A, R2 of S comma A, dot dot dot, RT of S comma A for all S and A. And this will be just S1, A1, S1 dash. SR, SA, something like this, S2, A2, S2 dash, and so on. Okay. So it's like it's
Yes.
not probabilistic, it's a random variable. At a time t, you will get this reward function or the reward vector depending on what S dash you sampled, right? Now Vt, again, Vt will also be a function of S comma A. What will it be? Compare these two equations and tell me what will be at Vt of S comma A be?
It would be max of A star QT S dash comma A dash.
Correct. Max of A dash Qt of S dash comma A dash. Again, there is a problem. See, the right hand side is just dependent on one variable, yes or no? Because I'm marginalizing out actions. Like we are maxing out actions. So it does not depend on A, right? Does it depend on actions? This is
No, we have a vector there for where we store the value of Q S dash for all these actions in the action space, and we are selecting the maximum of that vector. So essentially, it's not a function of any action.
A.
So
Correct.
it's just a max function, max of a series.
Correct. So this is two variable. This is one variable. So I cannot do this. So I define it for all A. This will be true. Then it's correct, no? Because that's how this equation is. For all A, the maximum is still the maximum. Yes or no? Look at the equation. The max over A dash is true for all A. Yes or no?
Yes, sir.
So for all actions, I will put the same value. For example, say S1, A1. This is the problem. See, the indexing and the time points will be matching. So I'll put index, sub-index here for the time being, S1, A1, like this. S2, A2, dot, 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 or rather S1 and S1, AK, like this. And then for all of these, the V value function will just have the max value. Say this is A max for the current state one, right? And similarly, this will just be, so similarly, you will have for the second state, you will have A max 2 and so on, correct? No problem. So this is again a S cross A vector. So what I tried to tell you is, so I can write this as Qt plus 1 is equal to Qt plus alpha t RT plus gamma times Vt minus Qt. So why did I take all this hassle to write this down is the question. This is because of this. So now to see if this converges, what do I have to do as the first step? Do you remember? Again, this is a stochastic differential equation, yes or no? Discretized version of it. We have done this so many times.
Yes.
You have to,
So we would separate the noise terms, and then we will introduce the martingale,
correct.
the expectation of the noise, and add and subtract, and then show that the expectation of martingale is 0, and
Correct.
yeah,
That it will track a. So let us try define a history term first. So that this history term is again the collection of Q0, say S0 This is a function S1, S2 dot 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 ST minus 1, right? So let this be a martingale with the history term. So what do I mean by history? So history is something like this. Say ST dash is a mapping from states, comma actions to states. Is this isn't it? So what does this mean? Can you tell me what does this mean? It means that say at time t, st of s comma a is s dash, right? This is a set of functions. Is this clear? Because we want to know it at every time point, yes or no? Remember, there was this s and I took an action. And based on the probability distribution s comma a, I reached s dash, yes or no? Clear? So I'm saying I have access to all these functions that took me from S0, say at time 0, at t equal to 0, right? For all states and actions, I will have S dash, yes or no?
Yes.
So if for all states and actions I have an S dash, can I not define a mapping from say S? So this is your S cross
Yeah, for
S.
all states that I have previously visited in my uh, in this trajectory, I can say that there's a function connecting.
Yes or no? Yes, that's what I'm saying. So because at every step I am going to visit all states. Yes or no? That's how I have defined synchronous algorithms to be. All states and actions I will visit. That is not going to be changing, right? At every time point, what is the only stochastic thing in this algorithm? Is the next state that I'm sampling for this reward function.
Yes,
Yes or
it's
no?
the only stochastic component, and because till ST, we know all the S dashes before that, so we can make a history function for which would depend on the T as well. It is not a function of S and A only, it's also dependent on.
Correct. So I am saying at every time point in T as well, parsing over all the states like this inner two loops that I have is going to be fixed. It will always happen, right? There is nothing stochastic about it. The only stochastic thing is this S dash. Yes or no?
Yes.
This S dash is the only stochastic thing, and that's what I am saving. As you are saying, I can save it as a form of a function. That's what I do. Okay. So if I do that, why did I do or take all this hassle? So this is the reason. As you were telling me, so let us write this term as say f of s a s dash. This term is f a s dash as rt plus gamma times vt minus qt. What will I do now? I will replace this term. So I know that the update is qt plus 1 is equal to qt plus alpha t f of st at, or rather I'll write t over here is a, just write ft because this is does not depend on ATs. Okay, fine. Some ft. What do I want to do now? I want to replace this stochastic term using the expected value of ft given the history plus ft minus the history. Yes or no? This is what I want to do. If I can write this way. I just added and subtracted this expectation.
Yes, and then we'll show its tracking and OD.
Correct. So this second term is the martingale, mt plus 1. So I can write this as qt plus 1 is equal to qt plus alpha t, the expected value of ft given the history plus the martingale. Very good. Now let me show you that the first thing I'll show you is the martingale goes to 0. The expected value of mt plus 1 given the history is equal to what? Tell me. The expected value
Yeah,
of
we
f.
have done this again and again, so it's
This is just a one-liner. By linearity, ft given ft minus the expected value of ft given ft, because this is the constant. Constant given ft. Okay. So this turns out to be 0. And that's what I want, right? I want the martingale to be 0. It's fine. Clear? Okay. So now I know that if that is true, it tracks the ODE. We have done this in great detail.
another general question.
Yeah.
Is that if we have any kind of stochastic equation where we have a noise term, so introducing an expectation over the noise term and then adding and subtracting and then always so we'll get
It
zero
will
only.
not, like, you have to define that event. The history event must be defined. That critically defined depends on the history. What sigma algebra is that? In our
Yes.
case, we can define that. Like if something is not a random process proper thing, then it will not happen.
Okay, got
Because
it.
it is an MDP, it has all these nice properties. That's why we can define this, and you will see that it will turn out to be that. That's a very good question, actually. So only if you define the next step in terms of the history terms, then only you can write it in this way. And then you can write SDE to be in this form. Because this is what we found out in the Borkar theorem, right? That this will converge. We had derived all the 6 conditions. Given the FT, the stochastic differential equation converges. Otherwise, if it is not having those properties, it will be difficult. There are no results for that. So, do you agree this will track this expectation? Right? Let's try to know what this expectation is looking like. So now tell me what this expectation will be. Ft given Ft is the expected value of RT plus gamma Vt minus Qt given Ft. Okay, very nice. So this can be written as the expected value of RT plus gamma times Vt given Ft minus the expected value of So the basic idea is the current event must not depend on the future, right? That's what it must not happen. You're understanding, Antariksh?
Yes. Like because the MDP has the property, the Markov property that it only depends on the next state depends on the previous state. That's okay. But if there was a process, a stochastic process where this was not true, the Markov property
This was,
didn't hold.
see, Markov property is also that not that much important. If there was a stochastic process in which the future modulated the past.
Yeah, I got it. Like
Yeah.
the Markov property is another cherry on the top.
Yes, that is
We
true.
don't really need that, but it's important that it should be dependent on the history. That's what should.
Correct. It should be from the history. For example, if say, for example, you are predicting something from movies. So, but in movies, or you're trying to do something from, so you may be telling me, Dada, can you give me an example in which the future also determines the past? I can say, yes, definitely. In a language, in sentences, your future words do determine what your past words would be, right? When you write out a sentence, you can always predict a past word from the future words as well. So in those cases, this would not hold. It's a very good question. I really liked it. Okay. So now RT plus VT, that is all fine. So now the second term that I have, where is it? Okay. So now QT of S comma A. So now again, do you see that this term, second term, is a constant? You have to realize that it is a constant. Let me write out the first term first nicely. The expected value of reward SA S dash plus gamma times max over A dash Q. What was the operator? QT, correct. QT of S dash comma A dash given FT minus the expected value of QT of S comma A given FT. Do you agree? This is fine. This step is correct. Okay. Now you tell me, second expectation is over what? What is the random variable here? There's no random variable at all. Yes or
Yes,
no?
because we know QT.
QT is known. Similarly, only stochastic thing in synchronous, only stochastic thing in synchronous Q-learning is S dash. There's no such S dash, so I can just write QT of S comma A. Now the first term, do you see? It's the operator. It's the Bellman operator.
Yes,
It is the
Dada.
Bellman operator, right? It's TQ T at S comma A. Yes or no? This is how we define the Bellman operator. Because at this state, I know S comma A is known. S dash is not known. From history, I know S comma A. Right? History only tells me S comma A and nothing else. That's what is the important part. Rest of it was just for formalism. Clear? So in the matrix form, I can write this as TQ T minus where TQT of is a where this T operator is a mapping from S comma A dimensional space to S comma A dimensional space. Such that TQ of S comma A, what will it be? Can you tell me? This is the Bellman optimality operator. Bellman.
That's what's
Yeah, tell me. Muted.
yeah, so it's QT plus one of uh we can write it as QT plus
TQT is just putting the values in this place, no? Q. This is the Bellman operator, yes or no?
yes.
So given an S comma A, I will update the Q value function using this operator every time.
Yeah, that's why I said QT plus one.
That is true. This is, you can write this as, if you put qt over here, t over here, you can write this as qt plus 1. Okay, fine. So now I know the Bellman operator. So now I see that this is equation 1. From 1, I know that the ODE tracks the ODE, the ordinary differential equation, TQT minus QT. So now you tell me, so if this at fixed point, QT dash is 0, therefore TQT equal to QT star. At fixed point. So now my question is, does this fixed point exist? What can I do to say if the fixed point exists or not? Any idea?
That we can use the concept of contraction, I guess.
Correct. Very good. Banach's fixed point theorem. We can say that. So Banach's fixed point theorem, just state it here. If an operator C is a contraction, or in other words, or CV minus CU is less than equal to gamma times or cap, or say lambda times UV minus U under any norm, then there exists unique X star such that Cx star is equal to X star. This is the Banach's fixed point theorem. That is 2 points here. You project, you go closer, you will end up going to the X star point. Yes or no? Your distances keep on decreasing as you apply this Banach operator. Now let us try and prove this. At the end of the talk. Okay. So proof TQ is a contraction. Can you tell me how do I prove that? So first, when I need to prove something, I need to start from the definition is the idea. So let us start from the definition. TQ. So first two things. First, what will I have to do? Tell me. First step is select Q1 and Q2 as two Q value functions. This fine? And then what will I do to prove a contraction? TQ1, I have to prove, we have to prove this, right? Minus TQ2 under a particular norm is less than equal to some constant C, Q1 minus Q2. And I have to find out what norm is this, what norm is this. That's what I have to do, right?
Yes.
Are you following? So now let me do that. So what is TQ1? Say for a particular state S, A. This is the expected value of the rewarded SA S dash plus max of A dash. I hope you're following. What can I write this as?
Q1 of S dash plus gamma max of A dash of S dash comma A dash.
Q1 of. Right? So similarly, PQ2 of S comma A will be is this fine? Two equations I wrote. Now I subtract them. What do I get? TQ1 of S comma A minus TQ of SQ2 comma S comma A. What will I get? S dash. Then
And I'll get Q1 of max of A dash, Q1 of S dash comma A dash minus max of Q2 of S dash comma A dash.
good. So now I take mod on both sides. If I take a mod, I can use triangle inequality to write gamma times now I come under serious trouble. This is the catch. So this is fine. This step is fine, right? I just used triangle inequality. This is fine. Now, what is the goal that I have? Can you tell me? See, I will tell you what the result I'm using, and then I'll prove the result a little later. Then it will be easier for you to follow instead of. Now, the result that I'll be using is this. Max of reason next. Next lemma. Okay. I say that I take the max outside the norm, the absolute value. This is true. I say that this is true. So if I tell that that is true, now what can I do? Can you tell me? I'll tell you why it is true. For the time being, assume that it is true. Then, are you following?
Yes. I was just wondering if we could write use the again the object equation that we were doing Q for S dash.
I can again max out over S, no? So if I max out over all the
I
states
can
as
I
well,
can I can max out over S dash as well.
correct. So you can max out as S dash as well, and this will go out of the summation. And I will have gamma here. I will have a summation of S dash comma A over S dash, and this will go to 1. This is fine. Total probability. That now I have this equation. I have this equation P Q1 of S comma A, or this inequality S comma A. This is fine. This is the inequality I have. So now I tell you, if I have this inequality, what can I do? See, this is true for all s comma a on the left hand side. The right hand side, because RHS does not depend on s comma a. Do you agree? Right hand side is a constant. No, this is a constant. You're maxing out over everything. This is a constant. I'll wait for a moment.
Yeah, we did this last
Yeah.
time as
Okay. So what do you agree if this is true for all s comma a? It is true for the max as well. Do you agree? If it is true for all s comma a, it is true for the max over all s comma a also. Correct?
Yes.
yes. So we can write T of Q1 of max of S of Q1 of.
Correct. Do you know what this is defined as? You can do it as a homework. As the L infinity norm
Yeah.
or the max norm.
No, I know that the maximum turn is called infinity loop.
Correct. So you can prove it. So say for a vector
Yeah,
x
we
in
can do that. Like if we divide by the maximum, like for
correct.
say e to the
That's the
power n.
exercise, please
Yeah.
do it. And yeah, absolutely correct.
Or
So if correct. So x1, x2 dot xn. So if it's a vector in the n dimensional space, the L infinity norm of x is defined as max of xi I equal to 1 to dot n. And we know that LP norm is defined as the summation of xi to the power p 1 over p I equal to 1 to n. So all you have to do is p tends to infinity. So you see that hence TQ is a contraction. And thus TQ star is equal to Q star exists and is unique. Fine. Therefore, we have proved the convergence of Q-learning. Okay, so let us do the fun maths exercise now. And then the maths exercise is as follows. What did we take? We said that the absolute values maxes, if you take out the max out of the absolute value, that is greater. So all I am trying to say is lemma. I wrote it on the red color, so let me write it. Lemma is max of fx minus max of gx is less than max of fx minus gx. This is what I did. Look at this. This is what I want to prove, yes or no? Not here, sorry. This one.
yes, that.
This is what I want to prove. That when I take a maximum over a parameter inside an absolute value and there is a difference, compared to that, if I take the maximum outside and take all the computations, this is going to hold. So let us try and prove this. Any idea how can I do that? I'll just take a quick idea if you have. It's very, when you have these type of things, the best way to do it is this. So first I'll give you a simple example and then you can do that. Can you tell me if this is true? Max of x fx plus max of x gx is greater than max of fx plus gx. This will help you. You will remember this for your lifetime. Is this true? And if it is true, how can I prove it? It's very simple. See, do you agree? F of x is less than max of f of x. Max is defined as the maximum value of a function. Right? So any value of the other than that would be less or equal to. Similarly, g of x is less than max of g of x. Do you agree? Right? Now what do? I add them. So inequality doesn't change because I'm adding. I get this is what I get. Okay, so now again, left hand side, right hand side is a constant. Yes or no? A constant. Okay.
Yes.
So on the left hand side, what is it? True for all x. Therefore, it must be true for max as well. Correct? Agreed. Okay, so if you know this now, can you tell me how do I go about doing this proof? This is the idea because this was the first time. Now, how do I do? Thing on the left. So first of all, do you agree? F of x minus g of x is less than. Do you agree? The absolute value has to be greater than the function value, any function value. Absolute value is always greater or equal. Okay, so now if that is true, the max will also be greater. Even greater. Do you agree? This is fine. So I have got the thing on the right hand side. Now how to bring the thing on the left hand side? Can you tell me? So I've got this fx minus gx less than max of x fx minus gx. What do I do to bring the thing on the left hand side? I have already given the hint on the right hand side of the screen in the blue. Can you hear me?
Yes. So like firstly, we can write on the left hand side as greater than equal to f of x minus max of g of x because
Very good.
that's something that I can do. I can't
Okay.
directly write max of x of fx.
Correct. So okay, more than g of x, max of g of x is greater, right? Do you agree?
Yes. So on the left hand side, I can write f of x minus max x.
So this correct. So if this is greater, so I can even make a smaller term. If x minus max of f gx. This is correct. See, this is a larger term and I'm subtracting a larger term so that it becomes even smaller, right? So now you see, now it's very simple. So if this is true, this is a constant again. Do you agree? Constant.
Yes.
Yes.
So if this is a constant, this is the only function to optimize over. So I can say that fx minus max of x g of x, max of fx minus g of x. Look at this carefully now. When you look at this, what happens? So now it's true for all x. True for all x on left hand side. Yes or no? Right?
Yes. Yes. So it will be true for max of x.
Yes. Remember, this is a constant. So now I get this equation, max of x fx minus max of x gx less than max of x fx minus gx. But I'm not done. Look at this. I have a norm absolute value over here. So how do I bring in this absolute value? Any idea? I don't have an absolute value in this equation. This, say I say 1. How do I get absolute?
Triangle inequality.
No. See, this is very easy to get the absolute value. This is just a one-liner. Say I just interchange f and g. I can do that. Because these are at the end of the day some placeholder function. I can always rename them, right? So I will get max of x, g of x minus max of x, f of x less than max of x, g of x minus f of x. Do you agree?
Yes.
Swap. So now, but this is equal to f of x minus g of x. Do you agree?
Yes.
Done. Now it's done. Do you agree? Max of x g of x minus max of x. Right? Number 2. So combining 1 and 2, what do I get? What do I get? See, both a
It's the
minus
mod
b.
value.
Yes, both a minus b and b minus a both are less than means a minus b less than x and b minus a less than x means mod of a minus b less than x. Yes or no? Because if a greater than b, mod of a minus b is a minus b, else mod of a minus b is b minus a. Correct. And you're saying both of them are less than that. So therefore I combine 1 and 2 and get max of x, fx minus max of x, g of x is that max of. You can take an example of 2 vectors and try and do this and see. Okay. That proves that the Q-learning algorithm has a unique fixed point and it converges. So you used ODE and told it converges. Hence, I will not go to asynchronous Q-learning. It's a small thing. I'll do it next day. I'll stop with this linear function approximation case. So the linear function approximation is as follows. So again, till now, what did we do? Till now, we did tabular Q-learning with or without model. Yes or no? So now I tell you that the Q value function is the states and actions could be uncountable. It could be denoted by some features, and I don't know that as I have been done for TD learning algorithm. So this is what I want with linear function approximation. I want to map from states to actions to a reward function But what I have is for all states and actions, I have a feature vector. Feature vector in RD. So here S1, A1. So here in this case, states are S1, S2 dot Sn, and actions are A1, A2 dot AK. So for example, so just to represent this matrix. So now each of these could have D features. Some of them could represent state features, and the others could represent action features. The major talking point over here is as we have done before in value function v pi of s. What did we write this? Yes or no? This is what we wrote.
Yes.
So now I say that the Q value function for a policy pi as well can be written as pi transpose, or rather not for Q. I want to learn Q star S comma A W. This is what I want to do. Say I want to learn Q star. This is the end goal. Q star of, I want to learn a W such that I want to learn a W such that Q star is related as the feature matrix in this form. Is this fine with everyone? The features are given to me for every states and actions. I have D features. For example, cycling, velocity, acceleration, angular momentum, and so on. And the actions could be like what torque I give, a magnitude of torque, left, right, and so on. Right? And I see that I learn the corresponding weights to them. Okay. The same equation. There's nothing new. Can I go ahead and write down the updates now? Or do you want some clarification? So theta phi is a nk cross d dimensional matrix because you have n states and k actions, and you will have such nk rows and d features. So this is the nk cross d dimensional matrix. Okay, can I go ahead now?
Yes.
Okay, so we have understood this. So I will try to write down the Q-learning algorithm. So let's take this as the Q of S comma A. Okay, so now remember what was the loss function for synchronous. Again, this is synchronous with the linear function approximation. Yeah. What was the Q-learning objective? It was summation of, yeah, tell me.
Sorry. Yeah, S dash sampling from P given S and S dash.
The loss function, I mean, not the Q
Sorry.
learning. The loss
Sorry,
function.
summation S over S and A, 1 by mod of S into 1 by mod of A gives, yes, you're right.
This is fine. So I want to learn a Q value function such that it is, just a moment. Very fun. Okay. I want to learn an S comma A such that Q of S comma A such that it is equal to the Q star function. Okay, now I know Q of S comma A is what? How am I approximating it? In using linear function approximation? Minus phi Q of S comma A transpose W, yes or no?
Yes, sir.
Okay, so now this becomes a loss function with respect to W. And I want to update with respect to W. So I want to write an algorithm WT plus 1 as WT plus, or rather alpha T gradient of W loss of WT, not loss of W. Help me with the derivative then. DL dW will be, what will it be?
It will be one by S
1 by S A. Okay.
into Q
Summation of overall S comma A summation over all S comma A
into phi of S.
correct, because I'm taking a derivative with respect to W, so this is only going to remain. Very good. I have a negative term as well. So this is essentially an expectation, right? Where S comma A is sampled uniformly between 1, 2, dot, nk. Yes or no? So you S comma A is orderly sampled. There's nothing, because this is the average of what? Q star of S comma A minus phi transpose of S comma AW into phi Q of S comma A. Clear? They are WT. So I will have WT over here. Very nice. So now I have a problem. What is the problem? Not known. Okay. Not known. Fine. So what should I do? Again, I can write this as the expected value of yes or no?
Yes.
Okay. I just wrote the Bellman optimality equation. So I wrote the Bellman optimality equation. Now this is equal to two expectations, or rather both expectations can be merged together, where S dash is sampled from S comma A. Rest is all the same. S dash plus gamma times max of star of S dash comma A dash minus phi transpose WT by Q of SA. Okay, so now again, as we have seen that this algorithm converges because Q star is not known, I can write an estimate of QT of S dash comma A dash, which is phi Q transpose of S dash comma A dash WT. Do you agree? Noisy estimate.
Yes.
We have seen this converges already. So now this is expectation of reward S dash. So this is the derivative of loss with respect to W. That's gamma times max of A dash. Pi star, pi transpose Q, S dash A dash, WT minus phi Q JWT into phi Q of S comma A. Very nice. Now, as soon as I get this, so there's all negative terms I've forgotten to write. This is negative term. So what will I get? WT plus 1 update to be WT plus alpha T is A S dash plus gamma times max A dash. So I can write STAT A dash. They're not required. SAS dash max of pi transpose Q. Okay. Is this clear?
Yes.
So now as T tends to infinity, W tends to W star. Hence you get Q star is equal to pi transpose S comma A W. So now if I ask you what is pi star of S, what will you tell? How will I get it? I'll get it as max over all actions pi Q star transpose star. Clear? Any questions? So asynchronous algorithm we'll discuss next time. And then we'll begin with policy iteration algorithm. So we are done with classical reinforcement learning algorithms. And now it's time for the last cherries on the cake. So any questions regarding the function approximation, linear function approximation thing? If you thought I hurried a bit. It's the same
No,
thing. I just
same thing we did there. We started off with the loss function. We had taken the loss function as uh, v pi of
tabular.
yeah. No, for the linear approximation for value function we did for TD0. That's for model free. So we did v pi of s we did v of like for any pi v pi of s minus phi transpose of w
Correct.
and we found out the then we did all the operations on it and then we did the contraction. Here we first proved the convergence and then we used that convergence result here.
Yeah, and then for not only prove that convergence, so this operation also has to be proved, but I'm not doing it. It's again a long proof if you have to prove linear function approximation as well. So this is done by where is this? At least the asynchronous one was done in a paper, seminal paper by these authors. Where is it? Synchronous, yeah, by Mello, Ryan, and Ribeiro. So first you saw linear function, normal Q-learning tabular case converges, and then we saw that we could write out a linear function approximation for that as well and hope that W converges as well. And it does
Yes.
converge. Yeah.
So we had made that table initially in the class that like model-based or free and tabular or tabular not. So we have done tabular, model-based and model free, and uh, we had done by then, and we also did non-tabular as well.
Correct. So only you're saying model based and non-tabular. See, it doesn't make any sense to do, like, even if you have model based and tabular, you can just write down the same equations at the end of the day. Because if you have the model, you can clearly write down this, right? This equation on the top. When model is there, you know the derivative completely. That's the idea. You would know
Yeah,
the derivative.
when model is there, I know the reward function.
Correct. So that case is like trivial. You can just put the values of Q phi transpose and take the derivatives. It's not going to change a lot of things. So we have done all of these cases. And next day we'll discuss asynchronous Q-learning algorithm next Monday. And I will see where we go from that. And asynchronous is like going to take around 10, half an hour. And then we'll go into classification. I'll discuss a bit of machine learning first before discussing policy gradients, a class and a half. I will discuss classification problems and so on, because that's the building block of using the reinforcement, the AI, the neural network in the model, and then giving out an action. That's the policy gradient method. We have already done policy gradient once. So do you remember where? We've done it in bandits. And I have implemented it as well. So yeah, we'll see you on Monday then. Stop recording.